Hello everyone. In this session we'll discuss about interrupts in ARM. Okay. So before going to discuss something about the interrupts which are related to ARM, let us see what is an interrupt and what is an ISO. So interrupt is any kind of signal which disturbs or which preempts the processor from its main task. Okay, and this signal can be generated either externally or either internally. Okay, so we can generate that signal internally, or else we can also generate that signal from an external source. Okay, but it will preempt the processor from its main task so that it will execute some other program. Okay, now what is this interrupt service routine? Now, as we say that whenever an interrupt is generated, then the processor will respond to that interrupt. Now, what it is doing? So responding here is nothing but it will execute a program which is related to this the interrupted device. Okay, so as it executes the program which is related to that interrupted device, then it is nothing but it is responding to that particular interrupt. Okay, so responding here is nothing but executing an program which is related to that particular interrupt. Okay, and that program is called as interrupt service routine. Okay, so interrupt is a signal which preempts the processor from its main task, and interrupt service routine is a program that the processor will execute whenever an interrupt is generated. So every interrupt will have its own ISO. Okay, now if you look at the architecture of ARM, inside this architecture you'll find one block that is vectored interrupt controller. So vectored interrupt controller is the block which will take the interrupt sources, or which will take all the interrupts from the peripherals, and then those interrupts are given to the ARM core. Okay, now this interrupt controller, that is VIC, can support a total of 32 interrupts. Okay, so and this block is connected to a bus, and that bus name is AMBA bus, which is advanced high performance bus. So this block is connected to AMBA bus because they wanted to reduce the interrupt latency. That's the reason this VIC is connected to AMBA bus. Instead of connecting it to VPB bus, this is connected to now AMBA bus, so that the processor core can access the registers or the block, that is VIC block, as faster as it can. Okay, so the main reason for connecting this VIC to AMBA bus is to reduce the interrupt latency. Okay, let us see the architecture. Now if you can see the architecture, now this is the peripheral bus. Okay, and so what is happening here, the incoming clock is divided, and then that divided frequency will be given to these peripherals. But when it comes to AMBA bus, as you can see that the same bus is connected to VIC and the same bus is connected to the ARM core. So the same frequency is given to this block so that it can access this block as fast as it can. Okay, so that's the reason VIC is connected to AMBA bus, which is a high-speed bus. Okay, now as it takes 32 interrupts, now these interrupts are classified into three categories. Okay, FIQ and then IRQ. Basically it is IRQ and FIQ. Now IRQ is again classified into two more types, that is vectored IRQ and then non-vectored IRQ. Okay, so we can say that it is classified now as three interrupts like FIQ, vectored IRQ, and then non-vectored IRQ. Okay, now all these interrupts can be the interrupt priorities can be changed dynamically. Okay, but basically the predefined priorities would be FIQ will be having highest priority, VIRQ will be having, that is vectored IRQ will be having middle priority, and non-vectored IRQ will have the lowest priority. Okay, and only one FIQ can be generated for a single program, and 16 VIRQs can be generated for a single program, and one non-vectored IRQ can be generated for a single program. So a complete of 18 interrupts can be generated within a single program, and LPC2148 supports a total of 21 interrupts. Okay, so here VIC supports 32 interrupts, but out of those 32 interrupts, now LPC2148 is supporting only 21 interrupts, and we can generate a total of 18 interrupts within a single program. Okay, so let us see the registers which are available inside this VIC, and all those registers are word registers. So we cannot access them by using byte or half byte reads, or half byte or half word reads and write. Okay, let us see some key points here, like VIC has 32 vectored interrupt slots. So VIC has 32 vectored interrupt slots, out of which we'll use only 16 slots in LPC2148. As I said that only 16 VIRQs can be generated within a single program, so it means we are using only 16 slots out of these 32 vectored interrupt slots. Okay, and every slot has a set of registers like control and a address register. Okay, and if we are using these slots, then definitely we have to program this control as well as the address registers. So every slot is provided with a control and address register. For example, if there is slot 0, then slot 0 will have control 0 and as well as address 0 register. So if we are using slot 0, then we have to program those registers. Okay, and the slot 0 will have the highest priority and slot 15 will have the lowest priority. Okay. Now let us see, these are the registers which we need to configure when we want to use interrupts in case of LPC2148. Okay, so these are all the registers which we need to use. Okay, we'll see about each and every register in detail. Now let us see some of the steps to follow for using interrupts. So if I want to use or if I want to generate an interrupt in LPC2148, then I have to follow some steps. Okay, so let us see that. First is we have to enable the interrupt. So enable the interrupt whatever you want to generate. Okay, and then select the interrupt type. So as I told you that they are classified into two types, so we have to select whether it is an FIQ or else an IRQ. So if it is an FIQ, then we have to write an ISR with this syntax like void FIQ underscore handler and a parenthesis and double underscore FIQ. There is no parenthesis here, sorry. And so if you are generating an FIQ, then you have to write the ISR with this syntax. Okay, but if you are generating a vectored IRQ, then we have to access the registers of vectored IRQ like control register and then address register. So as I told you that each and every vectored IRQ is allocated with a slot. Now if we are using any slot, then we have to program those registers like control register and address register. Okay, so but after programming this control register and address register, then we have to write the ISR with this syntax. As you can see, void ISR underscore name, this is user defined, and then double underscore IRQ. Okay, and if you are generating a non-vectored IRQ, then we have to access default address register and we have to write the ISR in the same way as we have written for vectored IRQ. Okay, so here ISR underscore name is a user defined name and then double underscore IRQ. Okay, so whenever we generate an interrupt, first of all it will check whether it is an FIQ or not. So if that is not an FIQ, then it would be vectored, it would be IRQ. Now inside this IRQ, again it will check whether it is vectored IRQ or else non-vectored IRQ. Okay, if it is a vectored IRQ, then one of the slot is enabled so that it will access those registers. Okay, if that is not a vectored IRQ, then the slot will be disabled, all the slots will be disabled, and it will directly access this default address register. We'll see what is this default address register as well as control as well as address registers. Okay, but we have to follow these steps in order to generate the interrupts in case of LPC2148. Okay, so let us see the first register, that is interrupt enable register. Now this is the register which we use for enabling the interrupt. So the first step is to enable the interrupt, so that is why we'll be using this particular register. As you can see, 21 interrupts can be generated with the help of LPC2148. Okay, and if you can see here, each and every interrupt is having a bit position. Now these bit positions will represent the type number of the interrupt. Okay, if you take here UART0, so UART0, we can generate an interrupt with the help of UART0 and the type number of the interrupt would be 6. In the same way, if you take this EINT1 or EINT0, now EINT0 will have the type number 14 and EINT1 will have the type number 15. So if you want to enable any one of these interrupts, then the respective bit should be programmed with logic 1, so that that particular interrupt gets enabled. Okay. Now we have one more register, that is interrupt enable clear register. Okay. Now if you want to disable any one of the interrupts, then you have to use this particular enable clear register. Okay. So if you want to clear something like UART0, then it should be programmed with 1, so that the respective interrupt will be disabled. Okay. This is similar like set and clear registers in case of GPIOs. Okay. So if you want to enable the interrupt, then the respective bit should be programmed to 1. in interrupt enable register, and if you want to disable the interrupt, then you have to program the respective bit with logic 1 inside this interrupt enable clear register. Okay, and these registers are used with the names VIC int en clear and VIC int en. Okay, now let us see the next step, that is after enabling the interrupt we have to select the type of interrupt. Now we can select the type of interrupt with the help of interrupt select register. Okay, and this is the name which we have to use in our program, that is VIC int select. Okay, so by using this particular register we can select whether the interrupt is acting as FIQ or else as IRQ. Okay, so if you are programming any of these bits to logic 1, it means that that particular interrupt is now acting as FIQ. Okay, so by default all these interrupts would be IRQs. Clear? So by default, in the sense a logic 0 would be by default in all these bits, therefore they would be acting as IRQs. So if you want to enable any one of the interrupt to act as FIQ, then the respective bit should be programmed as logic 1. Okay, and then you have one more register, that is IRQ status register. Now this register will give you the status of all the IRQ interrupts. Okay, if any one of the IRQ interrupt is generated, then the respective bit inside this register will become 1. Okay, say for example I'm using UART0 as IRQ. If that is generated, then the respective bit here will become 1. So it will just show the status of IRQ interrupts. Okay, and then you have FIQ status register. Okay, now this register will show only the status of FIQ interrupts. Okay, so what happens if I'm using this UART1 as a FIQ, then if this interrupt is generated, then the respective bit here it will become 1, indicating that one FIQ is generated. And then you have vector control registers 0 to 15. As I told you that VIC supports 16 slots in LPC2148. So each and every slot has a control register and a address register. Okay, so here these are the control registers. As you can see, vector control registers 0 to 15. Okay, for slot 0 control register 0, slot 1 control register 1, and so on up to for slot 15 control register 15. Clear? So you have to access this particular register. We'll see how to program this particular register. Okay, now if you can see here, out of these 32 bits we are using only 6 bits. Okay, and out of these 6 bits, the first 5 bits are going to represent the type number of the interrupt. Okay, so we have to represent the type number of the interrupt. Okay, and the next bit, this is for enabling the slot. Okay, so let us see. For example, assume that I'm using EINT0 interrupt. Okay, I'm using EINT0 interrupt, and I want to allocate slot 0 for this EINT0. Okay, I want to generate EINT0 interrupt, and I want to allocate EINT0 with slot 0. Okay, now the type number of this interrupt is 14. Clear? So let us see how to program. So I would be using control register 0. I would be using control register 0. If control register 0 is programmed, it means that that interrupt is now allocated to slot 0. Okay, now inside this control register 0, the first 5 bits will represent the type number. Now what is the type number of EINT0? That is 14. Therefore we'll be writing 01110. Okay, and by default all the slots will be disabled. So as I'm using slot 0, that has to be enabled. So this particular bit should be written as logic 1. Okay, so I'll be writing something like, in my program I'll be writing VIC vect control 0 equals 0x 0x and then 6 zeros to E. So this particular value will enable slot 0 with EINT0 interrupt. So this is how we are going to write, or we are going to program this control registers. Okay, then we have address registers, that is vector address registers. As I told you that every slot is provided with control as well as address register. So initially we have seen how to program the control register. Let us see what actually this address register is going to hold. Now this address register will be holding the address of the ISR. Okay, so for example, if I'm writing an ISR for IRQ, now the address of that particular ISR should be written into this particular register. Okay, so if I'm using with control, that is slot 0, then I have to use VIC with ADDR0 equals the ISR name. Okay, so here it is similar to array name. Array name will give us the base address of the array. In the same way, ISR or else function name will give us the base address of the function. Okay, so what I have to do is I have to initialize this register with the function name, so that the address of the function will be assigned to this particular register. Okay, so vector address register will be holding the address of the ISR. Okay, now if that is not an IRQ, okay, if that is not, if I'm generating an interrupt, no, that is not an IRQ, then definitely the last would be default vector address register. That is nothing but it would be a non-vectored interrupt or non-vectored IRQ. Clear? So if you are generating a non-vectored IRQ, then the address of non-vectored IRQ ISR should be initialized with this register, or should be initialized to this register. Okay, so VIC def vect address register should be initialized with the function name or ISR name of the vector, non-vectored address register. Okay, now it will be holding the address of non-vectored IRQ ISR. Okay, now apart from all those registers, we have one more register, that is vector address register, VIC vector address register. Now this register is not similar to the registers which we have seen, that is VIC vector address registers, which are under the slots. Okay, now what actually this register means? So if an ISR is executing, okay, if the processor is executing an ISR, then the address of that particular ISR will be in this particular register. So while the ISR is executing, now this register will hold the address of the ISR. So until this register holds the address of the ISR, then the control remains in the same ISR. Okay, if this register is holding the address of the ISR, okay, then the control remains in the ISR itself. It will not come out of the ISR. So what we have to do is, as the ISR is executing, now this register will hold the address of the ISR, and at the end of the ISR, we have to initialize this register with a dummy value. Okay, it might be anything, but basically in most of the applications we use zeros, or we use 0 to initialize this register at the end of the ISR. Okay, so as soon as the ISR is executed, now the last statement will also be executed, that is this register is initialized to some dummy value, therefore it comes out of the ISR, as it is not holding the address of the ISR which it is executing. Okay, so while execution of the ISR, this register will hold the address of the ISR, so we have to initialize this register with a dummy value at the end of each ISR. It is similar like a RET instruction in case of assembly language, which will return the control from the ISR to the main program. Okay, so this statement should always be at the end. Okay, now we have one more register, that is protection enabled register. Now if you want to protect these VIC registers, vectored interrupt control block registers, then you have to use this particular register. If you program this particular bit to logic 1, as it is a 32-bit register, out of this we use only 1 bit. So if this bit is programmed to logic 1, it means that you can access these registers, that is VIC registers, only in privileged mode. If you are programming it to 0, then you can access these registers in privileged as well as unprivileged mode, which is your user mode. Okay, so apart from user mode, you have 6 other modes now where the processor will be transiting. Now those are 6 modes, those are all privileged modes. Okay, so only the user mode is a non-privileged mode. So we'll discuss about privileged and non-privileged when we talk about the architecture of ARM7. Okay, so let us see interrupt sources. So each peripheral device has one interrupt line connected to vectored interrupt controller. So all the peripherals will have an interrupt line. Now that interrupt line will be connected to the vectored interrupt controller, but may have several internal interrupt flags. Okay, so if for example if I take UART0 can generate an interrupt. Okay, but internally it may have more than one interrupt flag. Okay, so individual interrupt flags may also represent more than one interrupt source. Okay, let us see those interrupt sources. Now, as you can see, timer 0 can generate an interrupt. So timer 0 will have one interrupt source, okay, one interrupt pin, but internally it has so many interrupt sources like match 0 to match 3 and capture 0 to capture 3. All these can generate interrupt internally. Okay. In the same way, if you take UART 0, so RX line status, transmit voltage register empty status, and receive data available, and then character timeout. So all these can generate the interrupt. Okay. So these are all the possible interrupts that can be generated. Now let us see external interrupts. So interrupts which are generated using some external sources through external pins is nothing but external interrupt. So in case of LPC2148, we have four categories, or we have four external interrupts like EINT0, EINT1, EINT2, and EINT3. Okay, these are the four external interrupt categories. Why I'm saying category? Because each and every category will have some pins. Okay, so out of those pins, we can select only one pin to act as the respective interrupt. Clear? For example, say EINT0 is having 3 pins. Under this category, we have 3 pins. So out of those 3 pins, we can only select one particular pin to act as EINT0. Okay, so we have 4 EINT categories, that is EINT0, 1, 2, and 3. Okay, now if you want to use external interrupts, if you want to generate interrupts externally, then you have to access these registers, that is EXTINT, interrupt wake up register, and external mode register, and external polarity register. Okay, let us see each and every register in detail. Now we have a external interrupt register. Now it is an 8-bit register. Now out of these 8 bits, we are using only 4 bits, and the remaining 4 bits are reserved. Okay, now all these 4 bits are going to represent the status or interrupt status of those categories. Okay, so EINT0 will represent the status of, status is nothing but the current state of that particular interrupt is represented by using this particular bit. Okay, for example, say I am generating one interrupt and I have assigned that interrupt as an EINT0. So if that interrupt is generated, then this particular bit will become 1. Okay, and see, as soon as it becomes 1, now what we have to do is we have to clear this particular bit at the end of the ISR. If this bit is not cleared at the end of the ISR, then the ISR will be executed continuously. The control will not come out of the ISR because this interrupt is generated continuously. So as the interrupt is generating continuously, it will not come out of the ISR. So that's the reason we have to. So for that reason we have to clear these particular flags at the end of the ISR. Okay, so these flags will represent the status of the interrupts which are generated. Okay, next we have interrupt wake up register. Now if you are operating your processor in power down mode, then you have to use this particular register. Okay, so you can wake up the processor from the power down mode by using this register. Okay, for example, say your processor is in power down mode and you have programmed this particular bit to logic 1. Then external interrupt 0 will wake up the processor from the power down mode. Why? Because we have programmed this bit to logic 1. Okay, so if you want to wake up the processor with a certain event, okay, or else with these events, then you have to program the respective bit with logic 1, which will wake up the processor from the power down mode. Okay, and then you have external mode register or external interrupt mode register. Now this register is used for selecting the type of interrupt, I can see, like whether you want a level sensitive interrupt or else whether you want to generate a edge sensitive interrupt. Okay, so level in the sense until sorry, it would be for a duration. Okay, but whereas edge is for a shorter duration. Okay, so if you want to generate an edge sensitive, then the respective bit should be programmed as logic 1. If you want to generate level sensitive, then the respective bit should be programmed with a logic 0. Okay, say for example I want to generate EINT0 as edge sensitive, then this particular bit has to be programmed with logic 1 so that the processor will recognize only edge interrupts, only edge as an interrupt. Okay, and next we have is external polarity. Now after selecting the type of interrupt, I should also select whether they are active low or else active high interrupts. Okay, so that is done with the help of this polarity register. Okay, say for example, here I have selected edge sensitive. Now I want to program that edge as a negative edge. Okay, so if I want to program that as a negative edge, then this particular bit should be programmed to 0. Okay, so that it will select a falling edge as an interrupt. Okay, now if I want a rising edge, then this should be programmed with logic 1, so that it would be acting as a rising edge interrupt. Okay, so in the same way, this polarity 1 and polarity 2 and polarity 3 for EINT 1, 2 and 3. Okay, so this is how we are going to use all these 4 registers inside these external interrupts. So let us see a sample program which I am going to show you how to generate an FIQ with the help of EINT with the help of EINT 0. Okay, so that's the reason I'm showing you the pin cell register. I'm not showing you the complete register here. I just wanted to show only one bit here, that is P0.1. Okay, so I can use this P0.1 as EINT 0. Okay, but pin cell register should be programmed. It means these 2 bits should be programmed with 1 1. Therefore, it will P0.1. Now it will act as EINT 0. Okay, so I want to configure this P0.1 as EINT 0, and it has to act as edge sensitive. Okay, it has to act as edge sensitive, and whenever an interrupt is generated, then we want to transmit character F to the terminal. Okay, so we'll see how to do that. Okay, so this is the program. As you can see in my main program, pin cell 0, I'm using pin cell 0, and now it is initialized to a value D. Okay, which makes P0.0 to act as TXT, as I want to transmit something to the terminal by using UART 0. So that's the reason I'm making P0.0 to act as TXT, and P0.1 is now acting as EINT 0. Okay, and then for my main task, I'm using pin cell 2. Okay, which is configured as GPIOs. Okay, and then I'm using IO and DIR, which makes all the port 1 pins or all the port 1 pins of LPC2148 to act as output pins. Okay, and I'm using the UART registers like LCR, DLL, DLM, and then LCR. Okay, after that I'm using the external interrupt registers. As you can see, EXT mode register is now configured to 0x01. Okay, so 0x01, here it is nothing but I'm using edge sensitive for EINT 0 pin, which is nothing but your P0.1. Okay, so any edge, I don't know what kind of edge, till now I did not specify any edge. So an edge on this particular pin will result in an interrupt. Okay, now I'm specifying the polarity of that particular interrupt. Okay, so I'm writing here 0x01, which makes a rising edge. So for every rising edge on this P0.1 will generate an interrupt. Okay, so every rising edge on P0.1 will be recognized by the processor as an interrupt. Okay, and then I'm using this interrupt enable register. As this is our first step, we have to enable the interrupt. Okay, so as I want EINT 0, so I'm enabling this particular interrupt. Okay, EINT 0 is now enabled, and then I have to select whether it is acting as a FIQ or as IRQ. So as I told you that now we are generating an FIQ. Okay, so that's the reason I'm configuring this EINT 0 to act as FIQ. So I'm programming this interrupt select register. Okay, now I'm doing some task inside my main, that is toggling port 1. Okay, so when you run this program, what happens here is now this port 1 will be toggled continuously. Port 1 will be toggled continuously. Okay, but when an interrupt is generated, okay, when an interrupt is generated, and that interrupt, if it is EINT 0, that is through P0.1, okay, then what happens? ISR will be executed. So I'm writing my ISR void FIQ underscore handler and then double underscore FIQ. Okay, this is the start of my ISR. So I'm transmitting character F inside my ISR. So as one interrupt is generated, that is EINT 0. So what happens? The respective bit inside EXT INT will become 1. Okay, so if you write the same bit with again logic 1, then that particular bit will be cleared. So it means it internally does XOR operation. Okay, so as I told you that EXT INT should be cleared to 0 at the end of the ISR. If you are not clearing it to 0, then what happens? Then the processor will treat that this interrupt is generated continuously until this particular bit is logic 1 inside EXT INT. So that's the reason you have to clear this particular bit with again logic 1. Okay. So, and then as I told you that VIC vector address register should be written with a dummy value at the end of the ISR. So that's the reason I'm writing it with a dummy value. Okay. So while executing this ISR, VIC vector address register will be holding FIQ underscore handler ISR address. Okay. So until it holds this ISR address, it means that the processor has to execute the ISR. So that's the reason I'm writing this register with a dummy value at the end of the ISR. So as you write a dummy value, then what happens? It will come out of the ISR and again resumes the execution of the main program. Okay. If an interrupt is generated again, now it does the same thing. Okay. So this is how we are going to use interrupts in case of ARM and external interrupts in case of LPC2148. Thank you.